Morning, everyone. Morning, David.
Hello, David.
Let's give everyone a minute. Okay, maybe let's get started. So I mentioned yesterday, the that conference is in week of June 23rd. So given that, I don't think we are going to be pretty busy and tired that week. So I am going to cancel the meeting that is that week. Actually, it looks like I already canceled it. So the June 27th, I canceled the demo meeting. I'm still debating whether to have the 20th, the week before, just the week before that or not, right? But I guess we'll decide when we get closer. I am going to be traveling the beginning of June. So 6th and 7th, 6th and 13th, I'm not going to be able to make it. How would you guys like to proceed on that one? Do you still want to hold the meeting, or should we just cancel it? I guess we don't have to decide right now, but something to think about and be aware that I'm not going to be able to make it those 2 days. Again, anyway, the Zoom link is open all the time, so even if I don't show up, you're all welcome to join and discuss how the product is going.
Okay, so I suggest, David, we just leave it for now because June is 5 weeks away, 6 weeks away. And
Yeah.
maybe at that stage, we will be creating the part model for the assembly. So if we are, we might have some questions that we need to put to the rest of the group here.
Yep. Yep. I will keep the meeting for now, and then we can all decide what to do.
Okay.
Okay. Sigmund, how is your ICAS submission? Were you able to complete it?
Oh yeah, I completed the drafts, and yeah, I'm just finalizing the paper. Yeah.
Okay.
So, yeah.
Okay. Very nice.
Yeah.
Okay, so I see that Patricia is here. Patricia, welcome. I think you were on tap to talk about the work that the modularity Workstream has been doing. Are you ready?
Yeah, of course. So let me share my screen.
Yeah, please go ahead.
And then share it. So can you guys see what's my screen?
Yes.
Okay, cool. Um, you can see my slides. Oh, sorry.
Yes. Yeah.
Cool. I have two screens and I was not sure which one was sharing. All right, so we started to talk about this white paper we're trying to put together that I think has you know a relationship, like a tight relationship with the effort you guys are doing in this work stream as well. So I think there might be a lot of synergy and a lot of interesting collaboration we can do here. So I
So let me.
yeah.
I'm sorry to
Yeah.
interrupt you. I'm not sure if how much how
Sorry.
much the
Sorry,
the
1 second. There is work in my house. I'm going to close the door. Just so.
Okay. Yeah, so Patricia leads the newish work stream in OCP. It's HPC and modularity. So the work they have been doing is very similar to ours in the sense that they are trying to build and accelerated chiplets and looking at performance trade-offs. So in that sense, building a chiplet, it's very close to what we are doing. So I actually asked Patricia to talk to us and see what is common and what is interesting to this team and how they can help us and how we can help them. So just a quick intro on this. Patricia, sorry to interrupt you. Please continue.
No worries, thank you. Apologies for just running off, but there is some work on my house, and then it gets very, very noisy, so I want to stop them. Okay, so all right, so yeah, so I was supposed to clean these slides, but then I realized I was gonna leave it like they are because it kind of shows the thought process we went through with Arvin when we were trying to set up this. Yeah, so and as David said, basically we're trying to say, okay, go through the exercise of we want to build this system for artificial intelligence. What should we do? And of course, we don't have the the power, the people, the money to build it. But okay, let's do it as a thought experiment and as thorough as we can with the resources we have. And hoping that once this experiment is done, we can actually gather more strength. Okay, so the other clarification I wanted to make is that in our work stream, we care about modularity for HPC and AI. So there are so many aspects related with building a system in package that it doesn't. I mean, it's so many things. So we're not gonna maybe focus on things that are, the focus of other work streams. We want to only feature modularity and the fact that we can build different products with the same set of chiplets. Okay, so we started with this as to start the conversation. So and let me see if I can do a slideshow here. But then yeah, so basically we said, okay, if you have this set of IP and very basic IP, so if we have RISC-V cores, we have a Scratchpad, we have I/O, and we have an AI accelerator. How many different chiplets versions we can build? So we came up with these different chiplet, architectures that we could build. And remember that we are simplifying as much as we can, and also generalizing as much as we can. Trying to build from IP. And then once we have all these chiplets, what kind of system in package can we build? And then maybe we can say, okay, this system in package is for IoT, this other is for edge computing, this other is for HPC and AI, and so on. So that's kind of how we started. And then, so this is some diagrams that we were doing, but then we said, okay, so what can drive our chiplet, and then we looked into applications. So we found these two applications. There are other two. I basically talked with scientists in Lawrence Berkeley National Lab, and these two where they had a code that they could share, ready to share, especially this one that is open source. And I don't know if I can follow the link here. Yes, I can. But this has like the description of the architecture of the algorithm and how to run it. So we have access to this AI model, and we could try to to see if our architecture would work with this. So that's our first thought. Then there is this other one that is protein structure prediction, which is very popular these days, of course. And then there are other two that is more about materials that I didn't add in the slides. And then we said, okay, what is our next step? What do we do with this information? What do we do with these ideas? So we went through, okay, so let's do it in an FPGA. So we have this modular system for acceleration integration where we have these RISC-V cores, and then we can place accelerators and memory in any of the tiles. Basically replace the RISC-V core and then replace the different hardware accelerators in the tile wherever we want to put it, in any architecture, in any size we want, and then push it in the FPGA. And then as we were discussing this option, we were like, okay, so this is going to be difficult. There are so many nuances that we have to figure out. And we're gonna require a lot of people to make this happen. So we were like, okay, so what other way can we do it? And then I guess that's when we reached to the point you guys are at. That we say, okay, let's try to extrapolate and work with RTL and see and do models and evaluation. So basically we took this chip, which is from Gemini, which is a open source um, AI accelerator that has a spatial array, TPU-like, TPU style, that has a CPU, an accumulator, and a scratchpad. That's basically the IP we were describing before, right? And then they publish their area, and this basically we will try to define the size of the chiplet based on this area extrapolation. So we said, okay, in a 5x5 we can comfortable put a 64 by 64 spatial array, which is going to be the core of the AI accelerator. And then we can fit 8 megabytes of memory, of scratchpad memory in a chiplet. So we have these two chiplets very well defined. So we know there are some problems with this, and that's one of the things that we're trying to address first through synthesis and through synthesis basically, and making sure that we double check the size of the spatial array in a 5x5 and the size of the memory in the 5x5. And then the 5x5 was an arbitrary choice in a sense, but it's also to help build this modularity. So we might be able to get like a larger chiplet with a larger spatial array, but then this wouldn't allow us to play with the different chiplets as much as we want through modularity. However, we're still looking into these numbers, but this is the assumptions we did. Okay, so we said, okay, we defined the chip area. Sorry, go ahead.
Quick question, sorry to interrupt. So on your previous slide, is the host CPU right now in the chiplet, or you have separated out that outside of the spatial array?
Separated it, yeah. So
Okay.
yeah, so we're gonna have a different chiplet for to be the host, and then
Okay.
we have to figure out how much cores can we fit in a 5x5 or 25 by 25 or 25 millimeters square area.
Yeah. Yeah. Do you know what kind of communication bus this host CPU support?
In this one in particular, I cannot remember the name. This is related with FireSim, and so it's gonna be a tile link, I think, because this is rocket chip. Yeah.
Okay. Okay. This is the rocket chip.
Yeah.
Okay.
But we're not necessarily married with a particular CPU. I guess, of course, I think RISC-V would be better because it's open source. Yeah, but we haven't set that in stone. This is just an example to get the area numbers and extrapolate.
Okay, yeah, the CPU chiplet that we are building is based off of the Ariane RISC-V core,
Mhm.
and Sigmund has been working on that, modifying it. I think right now it's communicating over AAB, all
Oh,
between the CPU cores.
uh-huh.
That's why I was asking if right off the bat we are compatible or we are not.
Okay. So we are actually not that advanced, so we can actually start to think about being compatible. So I think
Yeah,
that's the point. So I took a note. So you said
yeah,
you're AIB.
yeah.
Yeah.
Also in terms of die size, we ended up with something around 10 by 10.
Yeah.
The reason being is on one side we have HBMs for memory storage, and those are 11 by 11, right? So 10 by 10 kind of, or actually we are probably at 11 by 11. So that lines up well in terms of physical design with the HBM. And second thing is, I think I saw some presentation somewhere where the 10 by 10 is actually the sweet spot in terms of die yield. Right? If you want to break up a big chip into smaller chips, 10 by 10 usually end up at around the sweet spot.
Yeah, I actually saw the same.
Yeah,
But I think, like this is still, these are just some estimates we did, and the reason why we did these estimates is because like in a 10 by 10, the spatial array we're gonna feed is gonna be humongous. It's gonna be at least 128 by 128, even
yeah,
256 by 256, and then the modularity concept kind of goes away. However, not necessarily. So I'm pretty sure we still, if we go with a 10 by 10, we still could play a little bit with modularity. So yeah, we're still
yeah,
open to that, and I think I agree. I agree.
yeah.
I've read similar things. Okay. All right, so we have these, we're working on validating these numbers. They might change after our validation, and that's the difficult part, right? Because we're trying to take the RTL and pass it through synthesis and get some numbers which are dependent on the technology. Some people are saying, okay, if we don't use 5 nanometers, 3 nanometers is not going to be valid, or it's not going to be an effort that is worth it. I do think that even if we work with older technologies, I think it's a very valuable effort to put the step on the door. But yeah, so I
Yeah.
guess we'll have to see. And then okay, so we have these, we did this, this is kind of a repetition of what we're talking about, where we can play with if we define 25 millimeters square, we can play with the different shapes of the chiplets depending on what is the purpose, especially if you are IO, maybe longer chiplet instead of a square one would make more sense. So that's why we came up with this, still keeping the 25 millimeters squares. And then just to give an example of what we could do, we said, let's take the TPU, the Google TPU example, which has 3 versions now, and say, okay, with the chiplets we got, we could build the Google TPU version 1, the version 2, and the version 3 in these 3 different configurations using the same kind of Lego approach. This is not necessarily correct, as if you guys are familiar with that, you know that the variation between these 3 systolic arrays is, for example, they introduce floating point in that to support training, and that changes a little bit because the systolic array for floating point is going to be completely different than the one that we would use for integers, especially in terms of area consumption and power consumption. So this is just to show an example of what we're looking after. And then I guess I'm gonna take a break here to show you. Let's see if I can find that somewhere open. I think I just deleted it. Let me see. I think I just deleted my PDF that I wanted to show you. But basically, yeah, I just deleted them and I don't have an example. I'm rerunning some things. But basically what we have is we can have, let's see. Let me just 1 second. I'll show you another thing and then yeah, so we started this white paper. We started this white paper where we saying this is just a draft. This is very drafty, so I wouldn't necessarily pay attention to many of the text. But basically what we have is we choose these 7 algorithms to start with before we target the big ones. And this one includes a transformer. And then we are going to profile the 7 algorithms, and that's the profiling is the part that I wanted to show you that I just deleted this morning. But basically, after we profile, we get a lot of information to build our chiplet to define the interface and the bandwidth. Here is an example, another example of the transformer. And you can see that I know the latency of the application, I know the utilization of the array, the efficiency, the computing, the bandwidth. I also know the bandwidth that I need for the scratch pads and also for the DRAM. So you see, this is the information I need to define all the interfaces for the different chiplets and
Yeah.
how they will be defined. And we're gonna do this for all the different applications. And then instead of giving you one example for the TPU, we're gonna have one for each of the different applications we choose. Like, or maybe, I don't know if it would be a one-to-one agreement, but we're gonna have, we're gonna try to have at least 3 different products built with the same building elements out of this exercise. So we're working in the bandwidth, for example. So we have some people working already, but we are trying to define the bandwidth for the chiplet, and we're going to see how that translates into the UCIe or a bunch of wires. We don't have anyone working in bunch of wires, so it would be nice to have a volunteer for that. Yeah, so we have bandwidth for SRAM. We're working on extracting the power required for the systolic array, for the scratch pad, for DRAM. So basically, in our variations, we want to show that for some applications, we don't necessarily need HBM. So we are fine with maybe DDR4, which we hope is a lot more easier to integrate. Then we're going to show that for others, we will need this different HBM, and then see how this reusability plays. And then the cost study and the yield study, which I think is going to be important. Maybe we have to start with this one, I don't know. But and what we hope is that after this cost study and yield study to validate the decisions that we made through this process. Yeah, and finally, I have this is the list that we did last meeting where people are volunteering work, but we still need a lot of help, and hopefully we can join some efforts with your work.
Yeah.
That's it.
I have a question on slide 10. Can you share a little bit more details about what does this table tell us?
Yeah, I wish you were there in last meeting and I had like these really nice plots where but I don't have it right now. Basically this is, for example, this is one example. I think I deleted
that. Actually, let me ask you some questions. So this data comes out of FPGA prototyping, or is it pure estimation about how the models will run?
This is simulation. This is simulation of how the AI algorithm runs in the accelerator.
So this is a simulation. So it like RTL simulation?
No, there is a model that is called ScaleSim, which is, I think, is very popular. A lot of people use it.
Okay. Okay.
I'm familiar with it.
Okay. So it runs through ScaleSim and gives you this output.
And then with that, you can, get all the plots that I just deleted.
Okay. And the bandwidths are what's the unit for the bandwidth? Is it
Words per cycle.
words per cycle? Okay.
And then you'll have to do some math and translate these depending on the frequency and the physical
Yeah.
of your system.
Yeah. Okay.
Yeah, so I think we're getting, I mean, we're going through that, and I guess the hard part of doing the hard work is in motion. So hopefully we can get something.
Yeah. Okay.
So are we planning to implement that AI accelerator you in physical design, like in the CPU, or
There is, so basically this would be an AI accelerator. So it would be a hardware specialized for AI, like the TPU, but yeah,
Yeah.
built out of chiplets.
Okay.
Yes, so I guess the answer is, that would be nice in the sense that we can add to our system those accelerators and make it a little bit more interesting, right?
Yeah.
Show a big die and how we integrated everything together. Because right now, Patricia, we have one CPU chiplet and one memory chiplet, which we're calling HBM, but it's not exactly HBM because we don't have all the models. It's just technically it's just SRAMs with wires going across from the CPU chiplet. But our focus is kind of show the workflow, at least the implementation workflow. I think what is good is with your work is we don't have the that initial architectural exploration that tells us these are the chiplets which you need, this is the bandwidth and so on, right? We guessed, we basically we kind of made up what the CPU chiplet needs to be and what the memory chiplet needs to be without any thinking going into it if that is good or not, right? We just pick something because we wanted to demonstrate the workflow. I think adding this initial exploration together, right? It's going to be very, very cool.
Excuse me, David, I have to drop. I've got another call I need to attend, but Justin is here, and if you have time at the end of this meeting, he'll go through with you some level of progress that we've made on the HBM4.
Okay.
You might be able to give him some directions on different approaches. Okay.
All right. Sounds good.
Bye.
Right.
Okay. Bye, Michael.
Yeah. Yeah. If we have a AI accelerator RTL, then yeah, we can make make it as a chiplet later with our source PDK or
yeah,
including the AIP driver. Yeah.
Patricia, I'm assuming you have you were showing the floor plan for this chiplet. You were saying it's open source. We have the RTL for that, right?
Oh yeah, it is open source.
Okay.
It is Chisel. Like this one is Chisel. So you have to go through the flow to get the RTL. But I have another one. I have some piece of Verilog that is Verilog. So you guys, if you guys have time, you could work with that one as well. So
Okay.
you guys are working with 45 nanometers, right? That's what you mentioned last time.
Yeah.
Yeah, we started with NAND 45, and one of the things we want to show is part of our workflow demonstration is technology, choosing a technology, right? The sizes will change, performance will change, and what that means. So we also looked at ASAP 7. I mean, kind of, we mentioned it. I looked at ASAP 7. I need to see if I can generate all the models. But yeah, so probably ASAP 7. I think last time in the majority meeting, ASAP 7 came up as a good choice. Actually, technically speaking, we don't have to match the technology between the CPU chiplet and the accelerator,
Yeah.
right? Especially,
yeah.
right, if the CPU is not that loaded, if the accelerator is what's crunching most of the time, we can show, hey, here's technology mix and match.
Yeah, agree.
Right.
All right. Yeah. Thanks. Yeah.
Yeah. So Patricia, you have not gotten to the point where you kind of have uh, uh, floor plan for the chiplet or any bump map or anything like that, right? It's just RTL and performance simulations.
Correct. We haven't gotten to that part. We have a couple of volunteers that are looking into how to run these. We have James from Cassia. He's
Yes.
looking into it, and then we have Boone, who is here, is looking into it. He's trying to see if we have some people from LBNL, and we're trying to see if we can get some of that. It's not easy though.
Yeah. No. Yeah. I agree. Yeah. I'm thinking how to. It's Friday morning. My coffee is still kicking in. I'm thinking how do we kind of help each other. Maybe we can talk offline because I don't have any ideas right now. And see what would be interesting. For those of you on the CDX side who would like to listen to the modularity workstream or help out, they're meeting bi-weekly on Tuesdays. What time was the meeting, Patricia?
Yeah, so it is at 9 a.m. 9 a.m. Pacific time.
Okay, Tuesday is 9 a.m. Pacific. If you go to the main OCP calendar, you'll see the call-in details.
Yeah, and I can drop the link here for our wiki.
Oh yeah, that would be great actually.
I'll just find it. It usually comes first in my Google search, and now it's not. So yeah, so this is our wiki, and there is some information there.
And you have a groups.io page as well, right?
Yes. I'm not that good with that one. I'll have to get better, but I have one.
Okay. Okay, let me actually, okay, I have it. Let me post the link as well. So anyone can go and subscribe to the mailing list, and you also see the calendar in there, I believe. Yep, the calendar is there. So you can subscribe to it, get the meeting invites.
Awesome.
Oh.
Yeah, thank you so much, David.
Yeah. Yeah, thank you, Patricia. I think this is very interesting.
No worries, thank you.
Yeah. Okay, let's switch to our regular programming. Sigmund, any updates from your side after your successful ICCAT submission?
Yeah, this week I just focused on the ICK, so yeah, I have no other updates. Yeah, I'm just working on the RTL, sorry, netlist integration.
Not
And
recently.
yeah,
Okay.
yeah.
Okay.
And yeah, we will show you the progress by next week. Yeah, after the ICAT submission. The due date
Okay.
is next Tuesday, so yeah, I can.
Oh, next Tuesday. Okay, sorry.
Yeah,
I thought that. My bad. I thought it's
oh no,
this
no
week.
response. Yeah, yeah.
Yeah. Okay. Okay.
Mm.
All right. Sounds good.
Yeah.
Okay. Let's switch then to the HBM part model. Justin, Michael mentioned you might have some questions. Hello, Justin.
Yeah,
Yeah. Okay.
sorry, I had to. Apparently, you have to unmute your mic to talk. Um,
Yeah.
yeah.
That helps.
Let's see. So right now it's not in part model form, but I'll share my screen. It's a Excel file, um, kind of similar to how we had with the HBM 2E, I think it was. Um, so right now I basically have, let me pull up this. So we have the footprint A, footprint B, and then right now I'm mainly focusing on the footprint A. So we have like all the pin numbers, their coordinates, and their name. Um, and then we have a general layout, or I guess a layout of what pins are what, like what they do, I guess. So far I've basically kind of broken out the pin number into the row number and column number. Still have the name associated with the XY coordinates, and then I've assigned to each terminal what the like region based on like the layout is. So we have all that listed out here. I guess what I'm looking to do is if it's the layout of it based on the XY coordinates, basically devise a way of uh, creating this pin structure, terminal structure, um, in an efficient way, but in a logical way as well. Previously, with the HBM 2E, we basically just made the structure without thinking too much about uh, what the terminals are or um, what their terminal names are or anything. So we're kind of looking to kind of create the patterns based on. So this is another view of the uh, bump map, but basically like anything like it's probably going to slow down, zoom down so far. Basically anything like in here would be, like this is like a D word. So like create the pattern for like the D word, and then we can use that to populate like all these other D word and A word combinations throughout here. I guess it's not necessarily that I guess need help with it. I guess it's just more of a seeing if that kind of makes sense to do it in that way. The general structure of the HBM4 of the bump map, I mean, it's pretty consistent. So like the through here is basically the same pattern repeated. Then there's a section here that is slightly different, and then it goes and repeats that same first pattern. Somewhere in here it starts repeating it again, but yeah, I guess plan is to create the patterns and everything in a way that it's easier to link the electrical data to specific terminal names or sections of the uh, sections of terminals, I guess, if you will. Yeah. Any thoughts or anything with that?
Okay, I I admitted myself too. Yeah, no, I think you're on the right track. HBM is very repeatable, has very repeatable patterns. So hopefully that simplifies the model quite a bit, especially all the ports. They're pretty much the same port repeated multiple times, right? What is it, 32 times? So that should be should ease some of your pains. This fairly big. What you were showing, like 16,000 terminals.
Yeah.
Yeah, that's
That's
gonna
all. I mean,
be
that's also including the no bumps, but yeah.
okay. So okay, it includes the no connects, but include okay. So okay, 10,000. What is it? 9,000. Yeah, that's still 8,000.
Yeah.
Yeah.
So hopefully with the way of doing the the patterns and everything will make it fairly simple. Like, I mean, if we did it the way we did it before with the HBM2E, just you're doing the patterns and everything in the smallest, most condensed way to represent the structure, then I mean that would be really, really simple. But
Yeah.
but then bringing in the logic and everything does kind of make it a little bit more complicated, but it still should be smaller in size than just listing out every single XY coordinate.
Yeah. Yes.
Yeah. Really, honestly, I mean, Michael had asked if I was joining this meeting to go over this, like after the meeting had already started. I was like,
Okay.
sure.
Yeah. Yeah. Okay. No, this is good. Yeah, I'm definitely interested to see what the final model looks like.
Yeah.
That's going to be very interesting.
I'll stop
Okay.
sharing.
All right. Okay. Thank you, Justin.
Yep.
Yeah, let me know if there's any. I don't see what I can help with, but any questions that come up, we can always discuss.
Sounds good.
All right. I think that covers the important topics I had in mind. What else is on your minds today? Anything that I missed? Anything that we missed to cover? Um,
Mm.
no. Okay, so a reminder, think about the month of June. And once we get closer, we'll decide what to do with the meetings. Otherwise, DAC week, if anybody's in the area or attending DAC, please do let me know. We should try to schedule some time to meet up at DAC and chat face to face.
Mhm.
Okay. All right.
Sure,
Well,
of course. Yeah.
I think that's it for today then, and we'll resume next Friday.
Right.
All right. Okay, everyone. Thank you very much.
Okay, bye-bye.
Thank you.
Bye.
Yeah.
Bye.